I'm going to try and talk a little bit about the nitrogen problem a bit, that as Paul alluded to. But then I'd like to end with some just different types of solutions, trying to dovetail in sort of a broad spectrum with the diversity of what Paul said, and then some just other things that are going on the Cape that need to be considered. The problem, as we know, and we always think about it, we always talk about nitrogen loading, although 10, 15 years ago nobody was talking about it. And now it's a global issue. The global coastal oceans have been swamped with nitrogen. The population's up around 6 billion now, and most of those people live within 100 miles of the coast. And most of the ones that live inland and on rivers where their effluent also goes into coastal water. So what we see now globally is in these small enclosed bays and harbors, you see that the problems that you can see right here on the Cape, you can see anywhere else in the world. The process is called eutrophication. It can be a natural process, and it also can be a human process. If it's human, we call cultural eutrophication, and that's really what we do here on the Cape. Paul showed this, actually, same graph. It's just, where does this come from? All this nitrogen on the Cape come from. This is sort of a typical graph. The top pie diagram shows all of the sources of nitrogen, and in that case, it's about 70% of the nitrogen entering coastal waters is from septic in this particular example. But it includes other things too, like forests and rainfall and things that we can't control. And so it's when we remove the things that we can't control and focus on those that would be part of our management that the relative importance of septic jumps up pretty much Cape-wide to about 80% or more. And as Paul said, yes, that's why we're focusing so much on wastewater. The other sources are important, and I should not be wrong. This is the Bass River system. I just want to give this is a gradient map of nitrogen in the Bass River estuary, where dark blue is very low concentrations, sort of like offshore waters of Nantucket Sound, and orange is 3.5 times higher concentration than offshore waters of Nantucket Sound. And I put this up for a bunch of reasons. One, this is the typical way that estuaries look. Low concentrations near the inlet, so frequently down near the inlet, people that live down there say, hey, everything's great. But up in the upper regions, when you start getting the middle reach and upper reaches, then things really aren't great at all. They're really pretty poor. And so with all of the debates and arguments about nitrogen, the relative importance of different sources, the one thing that is unequivocal here is that the only place all that nitrogen can come from, the 3 times higher levels in all of the water in the upper bay, the only place that can come from really is from the watershed. So that concentration gradient is something that we create. If we weren't here, it'd still be a little gradient, but pretty much the whole system would be blue. I should show one thing. The problem with managing these systems. Just show us a time. I'll make it a 20-minute system. I've shown this slide a lot. It's the basic point of it is that nitrogen is an important part to these systems' function. All life requires nitrogen. Your lawn requires nitrogen. You fertilize your garden so the plants grow and are more productive. And these estuaries and ecosystems are the same way. You put more nitrogen, they get more productive. But the problem is, unlike your garden, you can start putting in too much and then you start tipping the balance, the natural balance within the system. The first thing you start noticing is algal blooms. Periodically, the water will turn green for maybe a week or so and then go away. Over time, as we have more development, higher nitrogen levels, then what happens is the green stays longer. And then pretty much it stays all summer. And it starts even staying summer to some extent into the winter. And with that turbidity, what happens is it shades out the rooted plants, the grasses that live on the bottom, the eelgrass, and other plants that are critical for maintaining our resources in this area. Not because we're interested, everybody has to love eelgrass, but because people love the things that require eelgrass, like bay scallops, blue crabs, very many waterfowl species, overwintering species, or migrating species require eelgrass. And there's a variety of services that this provides for us. So it's not just that one plant, it is all of the other things that come along with it. And then at higher levels of loading, what happens is then we start seeing fish kills. we start seeing low oxygen levels in fish kills, and we start sometimes even smelling odors. And we see fish kills in the newspaper routinely now. When I first moved to the Cape and started working on this in the 70s, there were one or two ponds, salt ponds in Falmouth that you might see fish killing. Now it's Seine Pond in Yarmouth, it's Swan Pond, it's Upper Bass River, it's Little Pond, Great Pond, Green Pond, Warren's Pond in Falmouth. It's just on and on. McCoy Bay, Pompanesett Bay, it's all over the place. So the thing is, what I'd like to emphasize is that a little bit of nitrogen's not a bad thing, even a medium amount is a bad thing, but it's the too much. And it's our job to determine what is too much. Just show a couple of pictures. The upper left-hand graph is a healthy eelgrass bed. The lower right-hand graph is what happens to that eelgrass bed when we increase the nitrogen level. This is West Falmouth Harbor, where when the West Falmouth Harbor treatment plant Plume and established in the 90s hit into the harbor, it doubled the nitrogen load to the harbor because of that big effluent load, and within about 2 years we've lost about 60% of the eelgrass. So it's a nice experiment for us as scientists, and of course now that they've fixed that facility, the system is now in compliance, the system should be meeting its TMDL hopefully, and where we are is now we get a nice experiment to follow the recovery of the system. But this is one of the key things of demonstrating a very rapid linkage of shifts in when you add nitrogen on Cape systems. In contrast, in Pleasant Bay, when the new breach went into Pleasant Bay in May 2007, there was a very rapid decline, or increase in flushing and a moderate decline in the nitrogen levels in the main parts of Pleasant Bay. And as projected, from all of the work that had gone out there, that when that happened, that the bay would recover to some extent, and it has, and the eelgrass, when we lowered the nitrogen levels right here on the Cape, the eelgrass very rapidly began to recover and to expand. So we have both examples on the Cape of a happy story and maybe not so much. The other thing I'd like to point out that most people don't ever talk about is what really happens in these bays. The yellow shows eelgrass in Pompanesett Bay, patches of Pompanesett Bay there, in Nashby, and Barnstable, and what we see the yellow represents historic eelgrass distribution in the 50s. By the 95, there was no eelgrass left, and there was presently no eelgrass habitat left within this resource. In keeping with that, when it's lost a long time ago, frequently that means that the load got very high very quick a long time ago. Did, but now what's happened is the load has increased. We've now lost the animal populations that were there as well. And that's the circle right here, that normally you should be seeing animal populations of around 30 species or so of animals and about 500 individuals per sample. And what we're seeing in large sections of this bay now are 2 species with 16 individuals. In essence, there aren't any animals left in large stretches of this bay. You say, well, that's just not necessary. But it isn't wrong. Swan Pond, it's Seine Pond, it's parts of Bass River, again, it's Great Pond, Warren's Pond in Falmouth, it's parts of Little Pond, it's on and on and on. I can go all up and around the Cape. It's even parts of Pleasant Bay are this way, Muddy Creek, for instance. So it's not just a one location problem anymore. The problem has now grown from 1 or 2 systems, just algal phytoplankton blooms now, to wholesale loss of these resources. This is the same thing that Paul showed. This is macroalgae. It grows out in the bottom, and what happens is on certain conditions, they're right, you get a lot of production, you get bubble formation, they float to the surface, the wind blows them to shore. But just because you don't see them doesn't mean they're not there. They're there again in most of these bays, and they're just waiting to appear when the conditions are right. And that was 3 bays. This is Swan Pond, Swan River in Dennis. And all of the stuff you see on the surface is macroalgae, it's Coleoptera. And then this is Requoit Bay, where there was a large visualization event, we'll call it, years ago, where the macroalgae that is there each summer really floats to the surface and was along the shore. It was so dense that people couldn't get through to get out to the moorings. So it's a Cape problem now, and as some of the old timers will tell you, when I was a kid, I didn't really see them, so it wasn't really around, and now I can't get away from it. The status, in summary, the status of these systems. Worldwide, we've lost about 65% of our seagrass habitat in southeastern Massachusetts. We're approaching that. We've already lost half of our total habitat. Up and down the Atlantic coast, almost all of the estuaries are showing this is a scary one, more than 50% of the benthic animal habitat, which is the food source for most of our commercial and recreational species, has been significantly degraded or significantly impaired or severely degraded. Meaning, severely degraded means it's just not there at all. And worldwide, and certainly in the U.S., this is going to be the big item for the next 20 years. So what's needed is nitrogen management. That's what we're talking about. That's what we're here to try to promote. And how we do it, though, is not just through controlled watershed inputs. That's what you hear about, that's what you read about in the paper, but also what happens, you can control and manage these systems if there's a way to increase the amount of flushing out of these nutrients. So if you can accelerate the rate at which they're flushed out, it lowers the level in the bay, or if you put less in, it lowers the level in the bay. If you do them both together, then they both work in concert. And the way that we've been approaching this is to do these quantitative watershed assessments and models. Really, it's the assessment part that sets the threshold. The modeling is really just to provide a guide into the future. And this is the Massachusetts Estuaries Project effort. The Estuaries Project is set up to look at all 89 estuaries here, shown by the different colored dots, that reach from Duxbury out to Nantucket and Vineyard and over to Mount Hope Bay. We've completed almost all of the data collection on this. We've completed to final 44 of the technical reports, and we'll have another 12 done by this July. So we're moving along. We're sort of around the 80% completeness part of this project. Sort of move around quiet. Sorry, let's move around. Okay, the purpose of the project is to develop these nitrogen thresholds. So nitrogen thresholds are targets within the bay. It's an ecological threshold. It's not so much of a target for engineering as it's saying this is the level that you have to achieve within this estuary to have a high quality environment. The situation, though, is if you put a little bit more in a threshold sense, you put a little bit more in and you start seeing impairment. If you put less in, you don't really see improvement. So a major focus of the technical team in the Estuaries Project is to get that threshold as tight to the line as you possibly can to minimize overmanagement. We don't want to set thresholds that are too strict, thereby requiring the towns to build too much infrastructure, do too much work. So we have come up and worked with EP and EPA on two things. One, to ensure that we're as tight to that line as we can get, and the second thing is that it is not necessary to throw on an extra 20% just to be safe. The science is technically state-of-the-art enough that we don't have to do that, and we've been able to do that, and that alone, just that savings alone, could be 20% of the total cost of the project. We're talking $3 or $4 billion. 20% is it's $4 billion, $800 million. So it's a lot of money just on that sense. The other thing is to try to bring these new tools for cost benefit, really is what it is when you're going into the planning stage. You can use those tools to fine line and minimize again. Everything's minimizing infrastructure. We want to build as little stuff as we have to. And so in the 44 systems that are done, we've already moved into the selection and design of a solution path. So the trick is that when we're done setting a target, now we know what we can work on. We work then with the agencies, with the towns, and with their consulting engineers to try to come up with mixes of solutions for individual estuaries, although those solutions can cross estuary boundaries and watershed boundaries. But we have to focus estuary by estuary in the fix. And in doing that, then we can say, well, what if we do this? Would that work? But if we did something different, maybe we can save 10% of the money. Would that work? If they both work, we'll take the 10% cheaper. The fix, and a variety of towns are in that phase right now within the region. This is the list that we work from. It's just a general list. We can expand it or contract it. But in general, these are the 4 basic components that we think of when we think of solutions that related to nitrogen management. Ways to reduce nitrogen entry into these estuaries. And if you notice, wastewater options are at the bottom of the list. Now, my engineering friends will say it's because you scientists don't like engineers, but of course that's not the case. Everything that we see in this room is designed by an engineer. The point, though, is that we try to make with this is there's 3 boxes to be checked before you get to wastewater infrastructure. The first thing that you look at is this whole concept is well, if you can get it out faster, if you can flush it out faster, you'll restore the system. And we have many cases where that's already occurred. And so flushing it out is a good thing. The next thing we would look at is natural attenuation, which is that much of the nitrogen that enters the watershed never makes it to the estuary. About half of the nitrogen that enters any kettle pond on the Cape never gets out the other end of the kettle pond to get to the estuary. And if we can enhance that, then we can use that as a tool. Source reductions are obvious. Mainly it focuses on fertilizer, but the wastewater option is a centralized, decentralized approach. I think Paul did a good job. And I just want to show two estuaries, or two towns actually, of what they're actually doing. And the reason I'm showing them is because they're different than what you read about in the paper. Take the town of Mashpee. The town of Mashpee is applying a hybrid management approach. That's not their term, that's my term. I get paid by the word. So a hybrid management approach says, okay, we're going to look at source reduction. We're going to look at sewering within that oval at the bottom. There's reasons you do that is that's where most of the nitrogen just enters the bay by groundwater without any attenuation. Whereas up in Sandwich at the very top of that slide, only 8% of a pound of nitrogen that goes into the ground there ever makes it to the bay. So sewering, for instance, up there may not be the best way approach for managing this estuary. There may be other reasons to sewer, but it wouldn't be for managing the estuary. So that's one thing that's going on. Working a lot on wastewater infrastructure planning. But the other thing is the inlet management. Mashpee used to manage its inlet whenever it clogged, which meant that the water quality in the bay would go up and down depending on how occluded the inlet was to tidal flushing. Based on the results from this work, what's come out is if they can do annual dredging, it costs them a lot less. The permitting's a lot easier. The impacts on the estuary is a lot easier. And it lowers the nitrogen burden within the bay sufficiently so it maintains a more stable environment, thus saving them significant amounts of money. The next thing is, also in the same estuary, as you see those two dark patches at the bottom of the box, those were built to intercept the nitrogen coming out of the watershed and coming out of not just the box, but the watershed above those box, and they attenuate the nitrogen on its way down gradient to the bay. It's a passive system, but it's a natural system. Lakes do it, mill ponds do it, these artificial ponds do it. They remove nitrogen. And the final one in Mashpee is sort of working on oyster culture. It's something, it's a sort of a pet project of a bunch of us. But the reality is that as a cleanup phase within the Mashpee River, it actually has some merit because it can remove a significant amount of nitrogen. 3,000 pounds of nitrogen per year is a lot of nitrogen to remove, and that's a minimum estimate. Now, they're not up to that yet. They're not in the 3 million, but in the hundreds of thousands. But, you know, my favorite thing about this experiment, if it doesn't work, you can beat it. And the final piece is Parker's River and Lewis Bay in the town of Yarmouth. The town of Yarmouth is well deep into its conference of watershed management planning. And they have two main systems that are in the plan, although they have a third one. And what comes out is this is their sewer area. And what you see is, for those of you that know Yarmouth, the white that you see is within the town boundaries, the gray is not. And you see that colored area, that's the only area they're going to sewer. They're going to sewer the whole town. There's no need to. For estuarine restoration in this system, there's no need to sewer the whole town. In fact, Paul's estimate of about 40% of the watershed area on average would have to be, if you just did sewering and nothing else, only did 40%, that's probably not right. So the concept that in order to fix things you have to sewer everything is incorrect. Maybe if we did not have the tools to determine how much you have to remove, you might just be safe to sewer everything. But right now we're talking about limiting the sewering down, certainly to less than half of the load. The other thing, though, is that both Lewis Bay and Parker's River are in the system, and what they have is both systems have nitrogen impairments. This is Parker's River system, and the status is it's impaired. Lewis Bay is also impaired. It's lost its eelgrass. Parts of it has periodic algal blooms, it's periodic low oxygen events, it has fish kills. It's a pretty crummy system now. So, and you can see very high concentrations, 3 or 4 times. The impact is down in the upper reaches and then grading down again, standard pattern. But what we found when we did the analysis was that the blue line, the blue sinusoidal line, is the tide in Nantucket Sound, and the little tiny little red line is actually the sinus of the tide range, the tide cycle. In St. Pond, the fact that the tide in St. Pond is only about a quarter to 30% of the tide in Nantucket Sound means it's very, very blocked. It's very restricted, and what restricts it is Route 28 Bridge. So what we found was that if you widen the bridge, I didn't say soaring, I just widen the bridge, the system would meet present thresholds of current development. The problem in the town of Yarmouth is they have to still soar over in Lewis Bay and bring wastewater in. So what they're going to do is they're going to bring the wastewater in to Parker's River, where they already have a small treatment plant and a discharge site, discharge the water within Parker's River, and then source some of Parker's River so that they get the balance. And in fact, if they just widen that bridge and they soar what was in that first graph that the engineers had come up with, they can discharge within Parker's River. They don't have to go buy additional land, and they will meet the TMDL for both. We think Parker's River will almost certainly include Lewis Bay. And they will save tremendous amounts of money just with a little foresight of trying to not just say, well, we're only going to build wastewater, but to look at these systems holistically and to use all the tools that are available to them. How long does recovery take? Well, the bottom line is recovery, once you start doing something, occurs relatively quickly. You'll start seeing improvements very fast. It may take a very long time to see full recovery, but instead of seeing things get worse every year, we'll see significant improvements in the first 3 to 5 years. The only problem is that one catchphrase that I used, which was, it's 3 to 5 years after you start doing something. So it's time maybe that we start doing something.